Okay, so somehow I accidentally stopped the video instead of pausing it there. So we're going to keep going from where we were at. Where were we at anyway? I think we were at the point where I was saying where this whole argument comes from. Well, anyway, there's other ways maybe of thinking, oh, yeah. Okay, I'm back on track. Right. There are other arguments, okay? And in fact, I'm going to encourage you to take a look at Wikipedia. I know Wikipedia is not always considered the best source, and it's not. It's often not a great source, but for a lot of math stuff, actually, Wikipedia is a pretty reasonable overview of a lot of things. Like, math is not one of those controversial topics where you have to worry about people coming in and making claims that are, at least usually, you don't have to worry about people coming into Wikipedia and making unfounded claims, okay? So you can actually use Wikipedia as a good guide for mathematical ideas. Anyhow, if you go down on their page about the geometric series, they have a very interesting geometric argument for why this sum converges to what it converges to. And that may be a more enlightening way for you to think about this than to think about the way that we did it here. Okay, so their argument involves taking a square and cutting it up into a bunch of pieces and seeing what this geometric series set. Like, basically, this geometric series can be interpreted as these pieces of a geometric figure. The geometric figure obviously has a finite area, and in the limit, as you increase these, you're essentially just taking more and more of this figure, okay? So there's this very nice geometric way of seeing that this is what this converges to as well. So let's take a look at some examples of using this. So here would be one example of using this kind of thing. We can say, like, let's say that we want to calculate the sum from I equals 0 to infinity of, let's say, 3 times 3/4 to the I. Well, in this case, my A is going to be equal to 3, and my R is equal to 3/4. And I just take this formula and I say, okay, so this is going to be equal to 3 times 1/1 minus 3/4. And at this point, we're really down at the point where all I have to do is a little bit of arithmetic with fractions, and I'm done. So this is going to be 3/1/4, which is going to come out to be 12. So there we go. This actually sums up to 12. Nice. We're done. Now, the main thing I want to emphasize when you're doing this is you got to be a little bit careful here. So this A times 1/1 minus R, this is true if you start at 0 with your sum. But if you don't necessarily start at 0, then you have to compensate by cutting off the first pieces. So, like, let's say that instead I had wanted to calculate the sum from I equals 1 up to infinity of 3 times 3/4 to the I. Well, in order to do that, the way that I would figure it out is I would actually say this is equal to the sum from I equals 0 to infinity of 3 times 3/4 to the I minus that 3 from when I is equal to 0. And that way I could just apply the same formula that we did before, right? A times 1/1 minus R. And then I just subtract 3 off of it, so I would end up with 9 as my answer. And that way I would be able to just use the usual formula, A times 1/1 minus R. More generally, whenever you have to deal with one of these types of series, you want to be careful to make sure that you've actually got it written in the form with A and R carefully calculated before you just start throwing things into the formula, okay? And this is not really any big surprise probably to you, because the truth is, whenever you've got some kind of a formula, you got to be careful when you use it that you're plugging in the right things, right? I can't just take a take the quadratic formula. You cannot just take the quadratic formula and start plugging in numbers and assume you'll get the right answer. You got to make sure you're actually plugging in the correct numbers, that you're using the formula in the context for which it was made. Well, the same kind of thing is true here. You have to make sure that you're using the geometric series formula in the context for which it was made. One more thing I want to say here about this geometric series stuff, and that is the following observation. So you'll notice that what we've really said here is that for absolute value of r less than 1, the sum from I equals 0 to infinity of a r to the I is equal to a times 1 over 1 minus r. But this expression on the right-hand side, this is actually a perfectly valid function of r. Like, I can think of this as f of r equals a times 1 over 1 minus r, if I want to. And in fact, if I do that, I can even write 1 over x is equal to 1 over 1 minus r, and this would just give me x equals 1 minus r, so r is equal to 1 minus x. In other words, if I set a equal to 1, and if I set r equal to 1 minus x, then f of r is equal to 1 over x. So I can even express 1 over x in terms of one of these formulas, but that means that I can express this function in terms of an infinite sum. Give me just a moment again. Sorry about that. Okay, so we can express this function in terms of this sum. All I would need to do is to replace, why did I put r equals 1 over x? That's not what I meant at all. I meant r is 1 minus x, which I also wrote. I just wrote something totally irrelevant and wrong as well. So we can express this function, which is a fairly standard function, in terms of an infinite series. Well, at least we can do that some of the time. We can't do that all of the time, because remember, we would need to have the absolute value of 1 minus x. This would have to be strictly less than 1. And this means that 0 would have to be less than x, less than 2, in order to make this work. But, you know, as long as we are talking about that sort of thing, yeah, that's perfectly valid. And as a result of this, what we can say is that this function actually can be given a series representation. In other words, we have this closed form function, but this closed form function is equal to this series, at least for certain values of the variable. And this is a very interesting observation, and it's something we're going to come back to later. We're going to come back to this with a topic known as the Taylor series, because it turns out that many nice functions can be represented, at least on a portion of their domain, as a series expansion. Now, you might say, well, why in the world would we want to do that if we've already got an expression like 1 over 1 minus r or 1 over x? Why would I ever want to express that as a series? But there are reasons. There are good reasons why you might want to express the function as a series. And it turns out that those are not necessarily obvious right now, but there are excellent reasons for doing so. One of them is because, for example, when we're talking about differential equations, a differential equation is an equation for an unknown function in terms of the function and its derivatives. Sometimes it's much easier to come up with a solution in terms of a series expression. Another reason you might want to do it is because sometimes you're trying to just get an approximation for something. So we will see, for instance, that when we talk about, say, exponential functions, or when we talk about trig functions, the types of functions that you can't really just calculate directly, it turns out you can give a series expression for those types of functions, and then what you can do is you can approximate them by cutting off the series after a certain point. The idea is you say, well, if we know how fast the series is converging, then maybe we can get an approximation by just cutting this thing off after a finite point. And so in that sense, you may want to use a series expansion in order to get an approximation. Anyway, so I think this is enough about geometric series for now. So we're going to be looking at some other types of series and how you can analyze whether a given series is going to converge or not. Now, as I said, the unfortunate thing is that there's a lot of series where we can't necessarily say too much about them. Maybe we can say that they converge, but we cannot necessarily say what they converge to. So, for instance, geometric series, this is a special case where we can actually work out a closed form formula, by which I mean a formula like a times 1 over 1 minus r, where we can actually just calculate the answer using this nice, simple formula. That is not going to be true for series in general, even very interesting series. But we will at least be able to say whether or not they converge and things like that. And if they do converge, then we'll be able to use them in various ways. One last thing I want to mention. What is the Taylor series? How do you get it? Well, we're going to return to that later on. But one of the things that you can think about in terms of the Taylor series is it has to be related to the derivatives of the function in some way. In fact, we've seen something that is the beginning of a Taylor series before, back in Calculus 1, when we looked at linear approximations. A linear approximation is really the beginning of a Taylor series, because the idea is that if you were to take a function defined in terms of r by a series like this, look at what happens with the derivatives. The derivatives are all going to depend upon these coefficients. And so there's going to have to be a relationship between these coefficients in here. Well, okay, so this is a specific geometric series, but let's suppose that these coefficients varied. So let's suppose that we had something like, instead, the sum from I equals 0 to infinity of ai times r to the I. Then these ai coefficients are going to have to depend on what we want the derivatives to be. And essentially, Taylor's idea was just, let's compare the coefficients and the derivatives that we get with them. Let's compare that to what we want to get for the derivatives and match them up. And that's really where he got his series idea from. Now, he didn't just do that. He did a lot more than that. He showed under what circumstances the resulting series would be equal to the original function, and he gave estimates for it. So it's not like he just said, oh, let's compare the coefficients. That's a good first step, but it's not really enough to get the whole series named after you. Anyway, we will return to that later and also be looking at other types of series. So in the meantime, let me know if you have any questions, and I will talk to you soon.